Okay, so I am starting in, or we are starting in, on Unit 15, which is rate of reaction and equilibrium. Now, this is another one of those units that is just an introduction to what you might see later on if you go on in certain fields. But it is it's an important one because of the different uses. And so with reaction rate, you are basically seeing how long it takes for a reaction to happen, how long it takes for the moles in a solution or in a compound to react. And it can take a really quick time, like almost instantaneously, or or a lot longer than that. It just kind of depends on what you're doing. And the reason it's an important concept to know is that it is something that is used in the medical field, like determining how long it takes a medication to take effect in your body, or how long it takes for that medication to leave your body, so you know kind of how often to take it. It as how tells you how quickly maybe like you burn food or burn calories, how quickly a fuel burns, and those kinds of things. And so it's big. I remember, at least when I was in school, my biochemistry class, we did a lot of reaction rates, just like determining how quickly an enzyme would break down a certain protein. And so all those are areas where reaction rate is used, and it will go on from there in different fields. So anyway, things that affect rate, we've got 4 of them, and we'll go through those kind of in order, kind of pieces in these notes. But you've got concentration, which of course is how much of a substance is in a solution or in a substance. Temperature, of course, which remember, heat is a form of energy. A catalyst, which is something we have mentioned in like biology when we talked about enzymes. But and we'll get to it more, of course. And then the nature of the reactant. So what are the things that are reacting? And so like if I want something that is going to burn, and then I want something that is flammable. So what is the stuff? Oops. Okay, so now we need to talk about collision theory, because for a reaction to happen, you have to have a collision occur between two different compounds or two different molecules. And the collision theory kind of is an explanation for why the factors that we just talked about, why they affect rate. And in the collision theory, we have 2 main parts: collision frequency, which we'll talk about here, and then the collision effectiveness. So collision frequency is the number of collisions in a certain amount of time, it can be seconds or minutes or whatever it is, how many times particles actually collide. And this is important because a reaction can't happen unless the molecules come in contact with each other. And so 2 of the factors we've already mentioned on the first page affect frequency. Concentration, first of all, because concentration is the number of particles in an area or in a substance. If I increase that concentration, I have a much bigger chance of a collision occurring, because there's more of them packed in there. And then temperature, of course, because that we know a higher temperature will cause the molecules to move faster, which means they cover more ground, so they have the potential of coming in contact with another molecule, but also hitting it with good speed behind it. Okay, so concentration. So why does each factor affect the rate? So first off, in concentration, where you can have low concentration, high concentration. So in our little picture here, which container is going to have particles that hit more often? It will, of course, be this container, because there's more of them in there. So you have a much higher chance of actually having 2 things come in contact than if you have a small number. And you guys may experience this, like when you're in a really crowded place, like like down in the high school hallway, our one hallway, When everybody is coming out of class at the same time, then there's a high concentration of people, and there is a good chance that you will bump into someone else, that you will come in contact with them. Now, if you have to leave during class to run an errand, to go to the bathroom, there's not going to be very many people in the hall, if any, so that greatly decreases the possibility that you two will actually bump into each other. Obviously, unless you're being weird and do it on purpose. But more means more possibilities for contact. Now, that's concentration. And so if we're talking about concentration, or how it's measured, or how you can change it, a solution, of course, concentration is typically measured in molarity. And so you can just make something more concentrated. So like when we made our Kool-Aid, if you wanted to increase the concentration, you just dumped more Kool-Aid powder into your cup. With solids, concentration is more thought of in terms of reactions, at least in terms of surface area. So if you can increase the surface area, you will basically increase the concentration. You will raise the rate of reaction. So this is like saying, if I drop a sugar cube into my tea, or if I put a spoonful of sugar into my tea, what's going to react faster, what's going to dissolve faster? It would be the spoonful of sugar, because the particles, the individual pieces, are smaller, which means they are going to be surrounded by the liquid, by the tea, more easily. Whereas with the sugar cube, it has to spend the time kind of pulling it apart in order to get, to surround each little individual sugar grain. With gases, it is pressure. So the more pressure you put on a gas, the more condensed it becomes, which just forces those molecules to be closer together. Again, that means they're going to come in contact. Okay, temperature. So you guys, we've talked about it a gazillion times, but when temperatures are high, molecules move faster, which means that they collide more often, and which means that they hit with more force. So that's a physics thing, they hit with more momentum because their velocity is increased. And this is important because something we haven't really talked about yet, but it is important because they have to have the proper or enough activation energy. So when they actually hit, they hit hard enough. And so the opposite happens, of course, when you lower temperatures. The particles are moving more slowly, which means they hit less often, and when they do hit, they hit with less force. And so it greatly changes the collision rate, and it makes it harder to get to that activation energy. Okay, so now the next part of the collision theory, collision effectiveness. So things collide. Now, what's the chance that they actually will result in a chemical reaction? Because not all collisions do produce a reaction. That goes back to what we just said, the activation energy. And so you have to get to a certain amount of energy, and it's the minimum energy that the particles need in order to keep going to react. On this graph, the activation energy is the height right here. So that distance, you can read it over here, if there were numbers here, of course, you can read it over there on the y-axis, and that would tell you the activation energy, like how much energy needs to be built up. And it's just kind of a little bump. Now, we've looked at these graphs before, but we've typically just looked at them where you go right from reactants to products. So we've kind of looked at a graph like that. In the real world, there is that big bump. So in the real world, this graph, you'd start here, but you'd have a big kind of a bump, and then you'd get back to the normal space. And so that activation energy is something that reactions have to acquire, have to build up. So like when water is evaporating, the particles, the molecules of the water, at the surface of a pond are colliding, and every time they collide, they're either losing or gaining energy and momentum. And so when they build up enough, they have essentially built up enough activation energy. They have gotten to the top of the hill, and then they just roll on down. In that case, they turn to a gas and evaporate. But in a chemical reaction, they rearrange themselves and you get your new product. You can, with these reactions, still determine exothermic or endothermic, just like we did in our thermo chapter. And again, it just depends on the difference between your end point and your beginning point. So remember, you always start here with reactants and then you end with products over there. And so in this case, if products are higher than reactants, you've gained energy. It's endothermic. Exothermic would look a little different. You'd start a little higher, still have to build up energy, and then you drop down a little lower. So they both require this activation energy, but it still is kind of comparing the beginning and the ending point for just a quick way to tell endothermic or exothermic. Okay, so this activation energy. So how is that part of the rate? And it's, you could just kind of, it's kind of a visual thing, really. So if you have the graphs, it's kind of easy to see. But it's, think about like like running up a hill. It's going to take you way longer to get up this big hill over here than it will to build up or get up to this little hill. So the lower the activation energy, the smaller the activation energy, the faster the reaction time. And so it really has a big impact on that rate. Okay, so now how do you change that activation energy? This is where catalysts come in. Now catalyst lowers the activation energy, makes that hill smaller, because it provides kind of a detour or an alternate route for the reactants to take in order to get to the products. And so on that graph, the red little hill is the activation energy with the catalyst. The blue is without, so it's like the normal reaction. It is reaction as it just happens. And so you have, it looks, kind of looking at it, looks like you need to build up twice as much energy in order for the reaction to happen. And so our enzymes in our stomach are natural catalysts. They help your food to digest and break down much more quickly. Things like catalytic converters in car engines help the gasoline burn more efficiently, or help your engine actually use the gas more efficiently with a lower activation energy. And so the enzymes in particular are important to us. Otherwise, a food would sit in our stomach a lot longer because it would basically have to just decay in there. Now, on the other hand, an inhibitor, it's the opposite of a catalyst, so it raises the activation energy. And so if we are doing that, still start here with reactants, you start building up, but now we have to go way up before we come back down and end up where we need to be, where the products are. Inhibitors can be actual chemicals, things like fruit fresh that you would, like you can put on like apples to keep them from turning brown. That's a chemical inhibitor. Some medications have the word inhibitor in their name, like a proton pump inhibitor, like it kind of helps with your stomach. It stops your stomach from producing so much acid, slows things down. Just putting things in the refrigerator is an inhibitor because it slows everything down. So they have to just build up that much more energy. Okay, so now the last thing that affects the rate of reaction, or at least our four, kind of our four things, is the nature of reactants. And so it kind of depends on the things that are reacting. So we've got three kind of main classes. The most active metals will react faster, so the bottom left of the periodic table, so remember Big Frank. The most active nonmetals, excluding the noble gases, because remember they're snobby and they don't want to react, so that would be Pretty Flow is the most active nonmetal. And then anything that is labeled acid or base, any acid or base that is labeled strong is going to have a higher rate of reaction than a weak acid or base. And so, obviously, like I was saying before, if I want to set something on fire, I'm going to put gasoline on it and not water. It's just what you're actually working with. Okay, so here comes the math. So with rate of reaction, we do have problems that are what they call rate law problems. And these problems help you determine what happens to the rate as the concentration of the reactant changes. And so numbers wise, you can express this using the rate law expression. And so this little formula right here in red is kind of our basic, kind of our generic plug everything in formula, I guess is the word I was looking for. And in there you have several different parts. You have the rate, which is what everything's equal to. K is a rate law constant. That's one of the things that we will have to calculate. Then you have the concentrations. So if you're reacting with two different reactants, you have the concentration typically in molarity of those two reactants. That's going to be given information. And then you can determine the order of the reaction, which basically is like the exponents. What power are they raised to? The order is important because it can tell you how complex a reaction is. The higher the number, the higher the number, the more complex the reaction, the lower the number, the less. But it basically is telling you that if something is raised to the power of 1, if you double it, then the rate also doubles. Now, if it were raised to the power of 2, then it would be squared, and so the rate would be squared. It would increase exponentially. Again, this is something that you would see in a biochemistry lab, a pharmaceutical place where they're trying to determine how quickly will this happen, will this reaction happen, how much medication should we give this person in a certain amount of time, all those kinds of things. This is how they get like the dosages. Okay, so now determining rate law. And the next several pages we're kind of base everything on this. So just kind of hang with me if you're writing your notes here. But so determining rate law, there are 3 things that we are going to find. And again, we're doing kind of basic. You can do more. You can add more things in there to find, but we're just doing very simple reactions. But you will be given information. So you have a reaction here. So 2A plus 2B produces 3C. I can put real compounds in there. Again, kind of generic here. And then typically you will see kind of the trial results. And so they give you the concentrations of A and B because those are our compounds. And then they tell you how quickly it happens. So these are measured units over here, this rate. And so from that, you can then determine how that rate changes if you change the concentration. So if I change the concentration of A in the second trial, then the rate goes up, this much. If I keep that change the same, but then I change the B, the second reactant, then I see that the rate goes up even more. And so using that information, setting things up in ratios so that you can do some math and cancel things out, then you can find our variables, which will be the rate law constant, which will actually be the last thing we find, and then the orders or the exponents. Okay, so here's our same example. So, don't rewrite this if you don't need to. But so what it looks like if you plug things into the rate law is what I have there for trial 1, trial 2, and trial 3. So point 1, so this, and I'll kind of draw arrows. This might get kind of messy, but I just want you to see where everything's coming from. So that's where I get the rate. And then the concentration of A goes here, and the concentration of B goes here. And so what we're actually really interested in as far as solving goes are going to be these numbers to start with. And we will always start by setting up ratios and finding the orders. Okay, so here are the ratios that I chose to set up. So you want to set up the rate laws, your ratios, so that the concentrations will cancel, K will cancel, and then you're left with this one variable to find. So in this first ratio of trial 2 to trial 1. I always put the bigger one on top because it makes the math a lot easier. Then you have certain things that will cancel out. The K cancels, and then this 2 cancels. So I get rid of that. So I'm left with 0.2 over 0.1 equals 4 to the m over 2 to the m. So if you do the math, you plug everything in, you're going to get 2 equals 2m. And so math-wise, and I'm sure someone could give you a really good explanation on all of this, anything to the first power equals itself. So we can look at that and say m equals 1. Okay, so we found m, and then we still have to find n. So we have to set up a ratio where the m's cancel, or the concentration of A has stayed the same. And so the k's still cancel, cancel, and then the 4's cancel, so get rid of those m's. And so then I essentially have 0.8 over 0.2 equals 4n over 2n. And so you've got 4 equals 2n. And so again, math-wise, 2 squared equals 4. So I know that n equals 2. All right, so that's kind of the big part. And typically your orders are not going to be, for us, again, I know they can change. Typically your orders are going to, I will always have whole numbers, but they can be fractions. They can be bigger. We'll usually have, 1, 2, 3 for our m and n's, but I want you to remember, just kind of get the concept here. So we found m and n. Okay, so now, what is happening? Sorry, I'm struggling with my technology here. Okay, all right, so now we're finding K. So I typically will pick the first trial because that's easiest for me. But when you plug everything in, you're going to have 1 for the rate, and it's molar per second as the unit. And that changes, but I'll always give that information to you. And then I don't know K, so that's going to go in. So you can put X there if you want. I'm just going to put K. And then the concentration for A was 2. We said M was 1. So that's how I would put that in. And then concentration for B is 2. And then N is 2. So then when you do your math, you end up with, is it 0.1? Hang on, technical difficulties. It's 0.1. Okay, so there's a 0.1. Okay, so if you do the math, you end up with 0.1, still m over seconds, and then you multiply everything out. You're going to have K times 8, 2 times 2 to the 2 times 2 squared is like 4 times 2 is 8. Yikes, thank goodness I'm not your math teacher, right? And now the units up here, this is kind of a confusing part. Remember that this is m, that's an m, and this is m also. So I have m to the first and m to the second. So my units are actually m cubed over here right now. So I do this math, and so I'm going to divide. I'm trying to get K by itself. So I have 8 m cubed, that's a cube, and then I'm going to divide by 8m cubed, and so get rid of it all over here, and then over here 0.1 divided by 8. Let me see if I actually answered this on my paper because I don't have my calculator with me. Give me a second. Hang on, so sorry. All right, so you're going to get I'll start back up over here, 0.0125. Okay, so let's get our units now. Now, this is just kind of how I always work it. These units are, so you have molar per second over molar cubed. And so remember, when you have fractions and they're dividing, you have kind of this weird thing, but basically what happens is it looks like this. I'm going to write it up here. So you have molar over seconds times 1 over molar cubed So that goes away. This becomes a 2. And so your units end up being 1 over seconds times moles, or molarity squared. Okay, and that's it. And that is your value for K. Yikes, that was a lot to do. So anyway, so that is the math part. The math itself is not hard. We'll kind of do more practice because personally, it's always the units that I'm kind of iffy on. Okay, so now moving on, reaction mechanisms. So now, a mechanism is a series of steps that is kind of explaining all the in-betweens, what really happens between the beginning and the end of a reaction. Most reactions actually go through a number of steps before you get to like what we normally look at when we write reactions. In a mechanism, you have your steps listed. There is always a rate determining step. It is always labeled as slow. Like when you write out a mechanism, you always have one that is slow. You're told that it is slow, and basically they're telling you that that is the rate determining step. They may put numbers with it at some point, so you have actual times. We will just, label them either slow or fast. There will only be one slow step comparatively. The others will be faster. Okay, now within a reaction mechanism, you do have some parts. You have the compounds, but then you also have some that you don't see typically or ever, don't see them in the final reaction. And there are 2 of them, either the catalyst, we talked about that. Catalysts work in a reaction, but they are not part of the reaction. And they will always be in the first reaction as a reactant and in the last reaction as a product. If they're on opposite sides of the arrows, basically you cancel them out. Okay, so we get rid of them. That's why you don't see them in the final reaction. The other thing that gets canceled out are intermediates, which I have labeled there just as OA. I don't know why. And they are always formed in a previous reaction, and so you see them first as a product, and then you see them next as a reactant, and again, they cancel out. And so you have everything else, basically you just kind of check it all off. And so if you have 2 of something, you put a little coefficient 2 with it. If there's only 1, there's only 1. But it's basically, if they're on opposite sides of the arrow, they're going to cancel. If they're on the same side, they will add up. Okay, now with these reaction mechanisms, you can also kind of put a graph with them because of the high-low. And so with these, again, you're going to look at fast, slow, or fast. So if it is slow, remember that means it's going to have a much higher reaction rate than if it is fast. So this graph, this one, is what will represent that above reaction the best. Okay, so now chemical equilibrium goes along with the rate of reaction, and it deals with reversible reactions, at least to kind of get us started here. And this is where you have, first of all, like the big thing as far as what we see is this double-headed arrow here, which means that you have kind of a continuous cycle going on where the reactants, these are still considered, like we will still call these the reactants, if I can get my pen to right there, and these the products. And so the reactants form products, and then the products turn right around and form the reactants. So you have this kind of cycle that goes on. And you can reach chemical equilibrium when the forward and the reverse equation are taking place at the same rate. And so that's where the rate part comes in. And a lot of systems do this, and it is very often, kind of one of those dynamic equilibriums. You're seeing the change, or it is changing, but visually it is appearing to be just the same or staying still. But equation wise for us, again, the big thing is that double-headed arrow, but just knowing that it is reversing itself. Okay, so now with equilibrium, there's more math. So yeah, you're welcome. And the equations themselves, along with concentration, can be used to determine the equilibrium constant. And you set up another ratio, and it is always the products over the reactants, so the concentration of the products over the concentration of the reactants, and it includes two parts, or two states of matter kind of. It only includes the gases and aqueous solutions. Solids are not part of this. And so when you are writing these equations, you have your equation, you are given the concentration, or at least just, the setup is the concentration of the products over the concentrations of the reactants. If you have two products or two reactants, you multiply those two things. Any coefficients, because these are based on balanced equations, any coefficients become exponents. And so, so you just basically follow that format and plug them in. And so, of course, yay, there's an example. So when you are writing this, these are all gases, so they would be part of this. So you're going to have concentration of the product, which is SO3, and you put it in brackets because that represents concentration. I know it gets kind of like you're used to parentheses, but write in brackets, please. So concentration of SO3 to the second power divided by the concentration of SO2 to the second power times the concentration of O2. It doesn't have a coefficient. Remember, that's an assumed 1. Anything to the first power is itself. So pretty easy to plug in, and so if you're asked to just set things up, you just plug them in. Now, if you have numbers that go along with this, then you get an actual answer, and that can tell you which side is favored, or which side will be, well, the reaction favor, and this means which side will form more. We have more of the products or more of the reactants. So if you get a number for KEQ, which is the equilibrium constant, if it is greater than 1, the reaction favors the products. If KEQ is less than 1, then it favors the reactants. So we have, here's a reaction. N2O4 produces 2 NO2, and then the reverse happens. So first of all, what is KEQ? So KEQ, typically you write, I know the way I've typed it doesn't really look like it. Typically the EQs are like subscript. But anyway, so you're going to have the reactant or products over reactant. So you have 0.03, goodness, I'm struggling, 0.03 over 2 because of the coefficient, or let me start over, let me say that again, 0.03 to the second power over the concentration of N2O4. Okay, and then, so we find that is our setup, and then when we plug in our numbers, oh my goodness, I'm so sorry. Let me start over again. So this is NO2. Good night. Struggling kids. Okay, so then when we plug in the numbers, we've got 0.03 second power over 0.0045. All right, so when you plug all of that in, you end up somewhere, and I have my little cheat sheet here, so you end up somewhere around 0.2. So if you look at your number, you have a number that is less than 1, which means that the reactants are favored. So remember, this is still reactants and this is still products. So our N2O4 is the favored side, which basically means if you're looking at this reaction, it tends to be going more this way and just a little bit that way. Okay, so at any one time, you're going to have more of the N2O4 in the beaker, or wherever you have it. Okay, so now last but not least, this is a long unit, the Le Chatelier principle. So this deals with stresses that can be applied to these equilibrium systems. And Le Chatelier's principle says that if you apply a stress to a system in dynamic equilibrium, the system will try and relieve or try and balance out that stress. And reactions react to 3 types of stresses: concentration changes, temperature changes, or pressure changes. Catalysts have no effect on equilibrium. Remember, they only affect activation energy. So they can make it happen faster, but it's not, it doesn't make it happen faster one way or the other. Okay, so first type of change, you have change in concentration. So if you add more reactant, so if I add, let's say I add more of B over here, I add more reactant, the reaction will shift to produce more product. So I, kind of think of it like a seesaw. So if I add more on this side, then it's going to want to shift, want to try and make more of the other side so it can get back to equilibrium. And so it will favor the products. Now, if I remove some of the reactants, if I remove some of B, if I take a reactant away, same thing. So now it's unbalanced. And what does it need to get back to balance? It needs more reactants. And so it will shift that way. More products added. Again, you look at kind of how it will shift. This one will go back towards the reactants. Remove products. It will want more of them. So it will shift that way. And so don't get too bogged down and like, what is actually happening here? Just, just kind of try and visualize kind of a balance of what's going on there. Okay, change in temperature. So now you need to know exothermic or endothermic. Where is heat? Is heat being absorbed as a reactant, or is it released as a product? And so you'll have to have that information. And so if you increase the temperature, wherever it is, the reaction shifts away to absorb that. So if I increase and add this heat, so I add more heat, it will shift that way because it's essentially like I'm adding a product. If I decrease the heat, if I take it all away, it's going to shift this way to get more of that heat back. Okay, so I kind of jumped over this little part, but so this is an exothermic reaction because heat is a product. And then what happens when temperature is taken away? That's kind of what I ended with. It will shift to the products. It will favor the products. Okay, last thing. So now, change in pressure. So pressure is only going to affect gases. So if you have a system where everything is a gas, then this can be affected by pressure. So first thing that you have to know is, where is the pressure? And it is easy to do because you simply look at the number of gas molecules. So you add up your coefficients for the gases on each side. And so on this side, we've got 3 and 1. So I've got 4 gas molecules over here and just 2 over here. So I typically will just over here put a P for pressure. That's where the pressure is. And so then you just treat it like we were the other things. Treat it, in this case, as a reactant. So what would happen then if I decreased the pressure? If I took this away, I took a reactant away. So it will be favored. It will shift to try and make more of it to get back to where it was. Okay, so we'll of course cover all of this stuff in class together, but as you go through this video, or if you go through this video, feel free to ask me questions. Bye.